Hello and welcome to Getting Started with Stella. I'm Billy Schoenberg and I'm a developer here at IC Systems, and I'm very excited to be here with you all today to show you a little bit more about Stella. But before we get started, I wanted to go over just a few little housekeeping things, the webinar mechanics. The first thing that you need to know is that there's a little grab tab that you can use to open and close the GoToMeeting panel. The audio setup section allows you to test your audio. If you're not hearing me, raise your hand. Ha ha ha. But if you've got any questions, please make sure you submit them through the questions section as opposed to the chat. That way we can organize the Q&A session. So let's get started with today's topics. The first one is that I want to teach you a little bit about Stella. I want to show you what the tool looks like. I want to give you the 30,000-foot overview. From there, I want to give you an introduction to the modeling process. We'll talk about creating a reference mode, drawing a dynamic hypothesis, creating a stock and flow model, and analyzing model results. And I'm going to make sure that we talk about at least Stella Live and Loops that matter. And then finally, like all webinars, I want to make sure that I leave ample time, approximately 15 minutes at the end, for questions and answers. So without much ado, why don't I introduce you to Stella? And so what we're going to do now is pop open Stella here. And you can see that Stella is arranged in a certain way. At the top of the screen, we have our toolbars. And we call this one that I'm currently mousing over the Build toolbar. And in the Build toolbar is where we have all of our major building blocks, things like stocks and flows. And we call them converters, but sometimes you may have heard of auxiliaries. Ghosts and text boxes and images and graphs and tables and all sorts of things like that. The second toolbar here is the mode toolbar. This one lets us switch between editing models and looking at results and CLDs and things like that. Over on the right here, we've got a panel. This panel is always context dependent. You can see that you can resize this panel or you can undock it and move it and dock it on the other side of the screen, undock it and put it back on the other side. And one of the neat things about Stella Architect is that you can rearrange the view to look however you want it to look, and the software will remember the way that you had set up your interface to be convenient for you when you are modeling. Okay? And then in here in the center is the canvas. This is where we'll actually do the work of building our models. We might, for instance, put a converter down, and you'll see then that this panel over here on the right updates along with whatever we have selected here in the canvas. And so what I want to do now is I want to return to PowerPoint, and I want to explain a few things about the modeling process. So when we're building models, we start with a problem. One of the major tenets of the system dynamics methodology is that we model problems and not systems. And so within that context, well, what's a reference mode? A reference mode is a behavior over time graph that shows us the problematic behavior that we're trying to address. So all a reference mode is generally a line graph that plots over time the problem that we're trying to understand and change. From there, we develop what we call a dynamic hypothesis. This is a causal explanation for why the model acts the way that it does, or why the problem exists. So these tend to be word and arrow diagrams, or causal loop diagrams, or CLDs, that depict the underlying logic or structure of the model that we want to build. This is kind of an explanation for how we think the problem came about and how we think we might be able to address the solution. Once we've got our dynamic hypothesis, we then move into the stock and flow model creation process. And that's where we begin to quantify our model. We use our dynamic hypothesis, our kind of understanding of how the system works, and then we start to build equations that represent that structure, that recreate that reference mode. From there, we strive to verify the model. We want to make sure that the model is an appropriate representation of reality. Not only does the model reproduce the reference mode, but does the structure of the model have something to do with reality? If we're modeling, fishes, we probably don't want to see cows in that model. If cows are important for describing the behavior of fishes, there's probably something wrong with our model. And I'm describing this process in a very linear fashion. Normally, when applied, it doesn't happen exactly like this. You start with your problem and you develop your dynamic hypothesis. You start building a model, but then you go, wait a minute, maybe my explanation wasn't right. And you modify your dynamic hypothesis, and then you try and validate your model again. No, that's not quite right. Let me change my stock and flow model, which then sometimes means I change my dynamic hypothesis a little bit. So you step through this thing in cycles. But generally, or after you've verified your model, you work to analyze it, try and understand, why does the model do what it does? Why do we get this behavior? Where is this reference mode coming from? Why does this policy option, which is the next step, make a difference in the behavior of the system? And then finally, we come back to the main point here, which is solving problems, which means that we want to be performing policy experiments. We want to modify our model in some way, shape, or form in order to address the problem that we've exposed with the reference mode. So today, we're going to go through all of these steps, maybe not quite so much the policy experiments part, because we've been tasked with a problem. You didn't know that you were coming to a webinar today to get some work, but I'm giving you some work. Our goal is to understand the dynamics of population growth within a fixed area. Okay, so let's go back to our modeling process and let's start following the steps. The first thing we want to do is create a reference mode. Okay, and the first step in making the reference mode is to decide the time specs for which that reference mode plays out over. So if we look when we have nothing selected here, you'll see that we have the model settings panel and it tells us the run specs. And in the run specs, we can set the start time and the stop time. So we want this model to start at time 0. We're not anchoring this to 2020 or 1980 or something like that. Let's just start it at arbitrary time 0 and go to time 100. And our problem takes place over 100 years. We want to look at the study of this population of, let's call them critters, that we're going to model on an island and see how they develop over 100 years. So we set our start time to 0, our stop time to 100. Now, there are multiple ways that you can create a reference mode, and I'm going to show you a few of them. The first one, and I'm just going to delete this converter out of here, is to click once on the converter tool, click again to place it, and we will call this reference mode population. And you'll see that as I'm typing, if I make a spelling error, Stella helpfully suggests for us how to correct that spelling, so that if you're a bad speller like me, you can present your models in a way that others will be able to understand. So this first way that we're going to make this reference mode is using what's called a graphical function. So once we're done entering in the name, we can then click on the variable itself, and you'll see in the panel on the right, we have the ability to enter in an equation. And you'll see that there are a bunch of subpanels below it. And the subpanel that we want to go to is the second one, the graphical one. Okay, and we're going to check off graphical, and then we're going to use the function of the panel to make it bigger so that we can draw in the behavior over time graph that we expect. So this is the first way of making a reference mode, just kind of drawing in your expectation. So maybe I think, we start with, 15 or 20 critters, and then over time we build up and we plane out at 100. But I know a little bit more about this problem than you all. I haven't shared everything yet. We know that we start with 100 critters in our population. And, we roughly think the island has capacity for like 1,000. So let's change the range on this graphical function to go from 0 to 1,000. And then let's draw in our problem again. So this time I can start maybe up closer to 100. Our population begins close to 100. And then over time it goes up and then it levels out. So that's one way to draw in a reference mode and to create a reference mode. The second way to do it is to bring in data from Excel. So if we come to Excel here, you'll see that I've got 2 columns worth of data. I've got time values, and then I've got population values. And this is showing me, behavior over time. And so I can take these and I can copy them. And then I can come back into Stella, select the reference mode, and it handily brings me back to the graphical panel. And you'll see that there are 2 options here. I can look at this as either a graph or as a series of points. And I'm going to choose to look at it as a series of points. And then I'm going to click this lock button so that I can replace all of the times and all of the values with the data that I just put on my clipboard. So I right-click on the table header, and I hit paste, and now you can see that all of those values have been entered into the table. And when I come back to the graph view, you can see that behavior over time being plotted here. You can also bring in reference modes directly from Excel using the Excel connectivity that we have built into Stella that allows you to directly import from spreadsheets or CSV files. But that's beyond the scope of what I want to show you today. So now that we've got this reference mode put together, we're going to save it. We're going to do File, Save As, and we're going to name this Reference Mode. And then I'm going to make sure to save this in the appropriate folder. And that's right here. So now we've saved our reference mode. And if we were to go to the next step in the process, that would be to build a dynamic hypothesis. So to do that, we're going to do File, New CLD, New Causal Loop Diagram. And this changes the interface of Stella for you to be more handy for building these kinds of causal loop diagrams. You'll notice that the build toolbar has been reordered for you to be more conducive to building these causal loop diagrams. And so the first thing we want to do when we're building our dynamic hypothesis of this system is we want to start with the key variable of interest, the variable that's in the reference mode, which is population. So I clicked once on the variable button, and then I clicked again on the canvas to drop it, and you'll see that I've gotten a nice little in-place text editor. And so I'm going to change the name of this from name1 to population, and when I'm done editing, I can click away, and it goes away. So that you can see this easier, I'm going to zoom in, which is on the upper right-hand corner, and I'm just going to zoom in so that we can see a little bit better. I can do the same thing with the Command or Control keys and the plus and minus. A handy thing about Stella to know is that it runs on both Windows and Mac with a very similar interface. So our documentation is platform agnostic. And for the handful of those of you who are running on Linux, we actually do offer a Linux build. So continuing on with building this causal loop diagram, we need to start considering some of the other concepts that might come into play. The next one that I can think of is births. So I click on the var tool, I click again to place it, I type in births. And so now we wanted to depict the relationship between population and births. And we do that using the connector. Using the connector tool might seem at first a little difficult, but let me walk you through it. You click once on the connector, you click then and press and hold on the variable that you want to start from, and then you draw with your mouse still down to the variable you want to connect to, and you'll see that as I get close to it, it says, hey Billy, you want to connect to births, right? And it highlights births for you. And then I drop, and it's connected. And then I can adjust the shape of this connector by either playing with the thumb, or I can grab it at the connector end, go back close to the starting end, and redraw it. Okay? So now we've got population impacting births. Well, what happens when we have births? Well, births impacts the population. So let's make a second connector that links the births to the population. But that's just one part of the story. That's the process of making more critters. Well, unfortunately, all critters don't live forever, so we need to represent deaths. So we can then, again, draw a connection between population and deaths. You know, the more population we have, the more deaths we have. And that's a little hint as to what we're going to get to next, which is polarity here. And then obviously the more deaths we have, the less population we have. So these are our first two loops here. And now we want to go through and we want to mark the polarity. Because one of the neat things about system dynamics is that you can look at the nature of a relationship and infer something about how the behavior of this system will play out. So we know that as population goes up, births goes up. So we're going to mark a positive polarity symbol. Likewise, as births goes up, population goes up. So let's select that connector by clicking on its thumb and marking it as positive. But see here, it put that positive sign in a place that I don't really like. It makes it hard to tell, well, is that the deaths connector? So what I want to do is I want to move the placement of that polarity symbol to be inside of the arc. So now let's do population to deaths. As population goes up, as there are more critters, naturally, all else being equal, there are more deaths. And then as deaths goes up, what happens to population? Well, that one's a negative. I've selected the wrong connector. As deaths goes up, population goes down, negative. So again, I want to move that one to be inside of the arc. So if I wanted to make these loops stand out a little bit more, I could use something called a loop label. And you might be saying to me, hey, Billy, where's the loop label in the build toolbar? Well, you'll notice that a couple of the tools have these little drop-down arrows next to them. And when you click them, it opens up a menu that shows you some of the other tools that are available to be placed in a CLD. And in this case, we want the loop label. And so we click on it and put again to place it. And we're going to name this births. And the inner text for it is going to be R1, reinforcing loop, 1, births. And then I can actually select the variables and the connectors that are involved in this loop so that when I roll over this loop, it highlights. So you'll notice that I very carefully selected the thumb and of each connector and the two variables. And when I'm done, I double click. And now when I roll over births, you can see that this other loop fades away into the background so that we can focus on it. Let's do the same thing now with deaths. And this one is a balancing loop. How do we know it's balancing? As population goes up, deaths goes up. As deaths goes up, population comes down. The effect is opposite of how we started. And another way that we can add things to a loop indicator is by selecting the variables of interest, command, press and hold, and drag. And when we get over the loop indicator, you'll see the green plus, and you let go, and now it selects automatically for you the variables as well as the connectors between them. But this is just one part of our dynamic hypothesis. This is the part that demonstrates the growth of a population. We haven't done anything yet with the in a fixed area part of our problem. So let's add a new concept called crowding. Okay? And the idea here is that as there's more population, there's more crowding. And when there's more crowding, there's a whole lot more competition for food. And when there's a lot more competition for food, well, some of the critters don't eat, which means there's extra deaths. So let's draw those connectors in. Let's link population to crowding and crowding to deaths. And then let's set the polarities for these things. As population goes up, crowding goes up. As crowding goes up, deaths goes up. As deaths goes up, population goes down. So this is a second balancing feedback loop. So what I'm going to do is I'm going to put in a new loop label, and I'm going to call this crowding loop. And I'm going to select population, crowding, deaths, command, drag, and put it in the crowding loop. Very cool. And we'll name this one B2. And we'll save this now as our dynamic hypothesis. This is our general understanding of how the system works. We've got three feedback processes. We've got the critters being born, we've got the critters dying, And then we have the critters crowding themselves as they grow more and more and more on this island and start competing for more and more resources. So I think we have a generally pretty good idea of the system we want to build. So we're ready to go ahead and build our stock and flow diagram. To do that, we do File, New Model this time. That way we can build a model with equations. And so the first thing I want to call your attention to is this little x squared here. When you start the software, yours may be in something called map view. So instead of seeing an x squared, you'll see a globe. When you're going to build a quantified model, something with equations, you'll want to make sure that you're either in model view or suggest view. Today I want to be in model view. Map view is useful when you want to build stock and flow diagrams that aren't quantified, things without equations. So why don't you go ahead now and put your software into model view. The next thing we're going to do is we're going to get our run specs set. We want to make sure that we have the right start time and stop time and the right calculation interval, or DT, for the model. So this model starts at time 0 and ends at time 100. And we're going to calculate this model 4 times for each time unit using the Euler integration method. We're going to set the time units to be years. And now we've done the job of setting up our run specs. So now let's begin the process of building this model. And so the first thing we want to do is we want to represent our population. And one little handy trick to think of when you're building a model is you always want to keep your model about 5 minutes away from running. If you're putting down lots of structure and putting in lots of equations, but you're not running it all the time, you risk getting yourself all tripped up and getting ahead of yourself and having a really messy knot to untangle. So you'll see here today that we're going to always be putting stuff down, entering in equations, and running really quickly so that we get instant feedback on how our model is doing. So I've created this population stock, and I'm going to zoom in this time by hitting Command plus so that you all can see a little bit better. And you'll see now that it's warning, Billy. There is an equation that is undefined. And we can see that here also in the bottom right-hand corner of the run toolbar. We can see that there's an invalid equation and that population is undefined. So let's set up a definition for population. When we work with stocks, because they're accumulations over time, what we need to enter in as the equation is the initial value for population. So we're going to enter in 100. The next thing we want to do is enter in the births flow. So to create a flow, I click on the flow tool, I press and hold, just like I do with a connector. So right now my mouse is pressed down. And as I get closer and closer to the population stock, it highlights and it says, hey Billy, do you want to connect flow 1 to population? And I say, Stella, yes I do. And I let go. And when I do, it connects flow 1 to population. And now I can rename flow 1 to be births. And if I want to adjust my flow, I can grab the valve, and once I've grabbed the valve, I can grab the points and make it look exactly the way that I want it to look. So from our dynamic hypothesis, we know that population impacts births. So we're going to draw a connector just like we did in the CLD from population to births. And we can adjust the way that that looks by adjusting the connector thumb. But it's not just population and births that it's not just population that determines the births. We need something else. We need the birth rate. We need the number, essentially, of critters that each critter in the population has as children. So this is the birth rate. And we're going to define the birth rate as a percentage of the population. So we're going to say each year, we get 5% more individuals, or critters in this case, 0.05. And we connect birth rate to births. And now we can write our first equation, which is going to be the population multiplied by the birth rate. So let's think about this in our head. Let's be the human computer. We start with 100 critters. At the end of year 1, we should have 105 because our births is 5 because we're taking 100 multiplied by 0.05, which is 5, and we're adding that to population. Now, one of the neat things about Stella is that it helps you with your units and being dimensionally consistent. So we want to make sure that we use that feature to make sure that we don't end up adding apples and oranges when the units are apples or the units are oranges. So you'll see that it's telling us, it's saying, hey, warning, Billy, population doesn't have units. So I'm going to go to population, I'm going to give it units, critters, and then I'm going to click on births, and you're going to see the units are automatically filled in for me, critters per year. Why? Because the units for a flow are always the units of the stock divided by time. The birth rate is 5% per year. So we can write that in as 1 over year, per year, or we can write that in as per year. And when we do that, now you'll see that all of our warnings are gone. And now I feel safe and comfortable and ready to run the model. And so I do. And now the software pops up something new for us. It pops up for us the loops panel. This shows us all of the feedback loops in our model and helps us to understand where the behavior in our model is coming from. So if we look close at population and we look at the little spark line in it, we can see that we've got exponential growth. And what this panel on the right is telling us, it's telling us that we've got one loop, and if I highlight it, it shows it to us right here. And it's telling us that this loop, R1, is responsible for 100% of the behavior of the model. Very cool. Makes sense. The reinforcing loop creates exponential growth. So let's double click to end the analysis of our model, to go from explore mode to edit mode, and let's keep building our model out. What I'm going to do now is close this panel because I want more room to build my stock and flow structure. But if you feel like you need your panel back, you can always hit the little triangle button and bring it back out for you. But in this case, I want it shut for now. So I'm going to make a flow now for deaths, and I'm going to press and hold on the population stock, and it automatically connects that flow directly to the stock, and I'm going to drag out. And now this is going to be deaths. And how do we calculate our deaths? Well, we know that deaths is related to population. And let's make that look a little nicer. But instead of having a death rate, this time we're going to use the average lifetime. So we'll create a new converter called the average lifetime, or time span. Lifespan. And now if I want to get the panel back to enter in a value, I double click on it and it puts the focus directly in the equation editor. And I say that a critter lives on average for 30 years. So whenever you're writing an equation, you want to make sure that you write the equation and then immediately thereafter enter in the units. So now we can take this average lifespan and bring it into deaths and write the equation for deaths. So we'll double click to open up deaths. And deaths is going to be the population divided by the average lifespan, which is critters. Critters is population per year. Lifespan is in year. Done. No unit errors. So now I can run the model by going to the bottom left-hand corner here and pressing run. And you'll see now that in our loops panel, we have two loops. We have R1 and B1. R1 is still this reinforcing loop that we were looking at before. B1 is this deaths loop that we just added. And when I select both of these loops, and let me make this graph bigger for you so that you have a chance of seeing it, you'll see that the red loop, the reinforcing loop, describes more of the behavior of this system than the blue. The 50% line we draw as dashed. That way it becomes very clear for you excuse me, when a series or a group of loops of the same polarity describe more than 50% of the model's behavior. In this case, we have reinforcing growth, although less since we added the deaths, and that behavior is being described by R1, the births process. So now let's go ahead and let's add in our crowding effect. And to do that, we're going to start by creating a variable called effect of crowding on deaths. Okay? And this is going to be a variable that we're going to multiply into deaths that's going to modify deaths based on the level of the population. So we know that population impacts effective crowding on deaths, and we know that effective crowding on deaths impacts deaths. And I'm not the neatest modeler in the world, as all of my friends will tell you. But if we want to spend a little bit of time and make this a bit neater, we can do that by putting all of these connector thumbs kind of on top of each other, so that when we draw this out, we get a little bit prettier of a diagram. And then if, for instance, this name is bugging you, being on top of the connectors, we can press and hold on the name and drag it so that it goes on the top so that it doesn't cover up our connectors. Or if you want to edit this name, you can double click on it. And now I can hit return to insert a return character in to make this name look a little bit better. So now that we've got population, effective crowding on deaths, and deaths all kind of hooked up, we need to start entering in the equation. But we need to think for a minute. How are we going to calculate the effective crowding on deaths? Well, we need to compare the population to something to determine, well, how crowded is it? So the variable that we're going to compare to is going to be the normal population. So this is the population level at which you get the lifespan being the average lifespan. So let's say at 500 individuals, or 500 critters, is when we get the average lifespan. So let's connect the normal population to effective crowding on deaths. Now I'm going to jump ahead. Rather than defining effective crowding on deaths, let's define deaths. Double click on it to open the panel, and it's population divided by the average lifespan multiplied by the effect of crowding on deaths. So when effective crowding on deaths is 1, the deaths are the deaths that we would expect from the average lifespan. When it's less than 1, we get fewer deaths, which means creatures on average live longer. When it's greater than 1, when the population is higher than the normal population, when they're getting all crowded and tight and up close and personal with each other, well, then we get more deaths. So that gives us a little bit of a hint about how we want to define this function. Okay, we're looking for a function that, when population is small, that it's less than 1. When population is the normal population, it is 1. And when population is bigger than the normal population, that it's greater than 1. So we're going to use another graphical function here. But rather than doing it over time, like we did when we drew the reference mode, we're going to do it based on the population over the normal population. And the units for this are dimensionless, because critters divided by critters is no units. So now we go to the graphical function panel, and we check off graphical, and this time it makes the graphical look a little bit different for us. Okay? It sets up from 0 to 2 on the x-axis, which is population over normal population, and it sets up 0 to 2 on the y-axis. Okay? In this case, I don't want to do 0 to 2 here. I want to do 0 to 10. I want there to be a lot of extra deaths when the population gets higher than the normal population. Okay? So now we need to think about the shape of this relationship. Does it look like this? Or does it look like that? Or does it look like this? I don't know. So let's puzzle through it together. So as population goes up, we want the effective crowding on deaths to go up. So it's not this way. It's definitely this way. And when population is the normal population, when we get 1 for the x, well, what do we want for the y? We want 1. We don't want 4.26. So it's got to be something kind of like this, except we want everything here to be below. Okay? So there's a bunch of handy-dandy shapes in the graphical function editor that help us kind of puzzle through these. And in this case, I want to use an exponential growth shape, okay, for the effect of crowding on deaths. And so I'm going to choose that shape, and you'll see that it got rid of my really messy drawing. And then I can play with the curvature. And what I'm doing is I'm moving this curvature around, and while it's moving, what I'm doing is I'm looking to get the point 1, 1 directly on the graph, because that's what I want in this case. You know, so I got it close, 1 and 1.0002. So I'm going to click the Done button, and then I'm going to scroll back up so that we can see, and I'm going to go to Points, and I'm going to make sure that 1, 1 is directly on the graph. That way, when my population is my normal population, I get the average lifespan as the average lifespan. So I now have put together my 3 loops, okay? So I'm going to save this model, and I'm going to call it SFD for stock flow diagram, and I'm going to run it. And what do we see? We see now that we have 3 loops. So let's check each one of these loops against our against our dynamic hypothesis. The first loop is the crowding loop. Let's go to our dynamic hypothesis. There it is. Come back to our model. Our second loop is our births loop. Go back to our dynamic hypothesis. Yep, check. Good. Come back to our stock and flow diagram. Here's our deaths loop. Check it against our dynamic hypothesis. Yep, still there. Come back to our stock and flow diagram. No more loops. Wonderful. So let's now begin to interpret this plot that we see here of loop dominance. So we see in the beginning, we see that we've got a lot of red. You know, we've got reinforcing is covering this dashed line. And then we go through a period where the dashed line is covered by the blue, by this light blue, by B2. And if we remember, B2 is this deaths loop here. But B2 isn't, 50% of the behavior. So if I press and hold on this graph, you'll see that it tells me exactly how much each loop is contributing. So B2 alone isn't describing all of the behavior of the system. It's B2 together with B1. So when you're looking for loop dominance, you need to be making sure that you are not adding up loops of different polarities. It wouldn't make sense to say, well, this system is dominated by the births loop and the deaths loop. It doesn't make sense. But it does make sense to say that the behavior of the system at this point in time, at time 32.5, is dominated by both natural deaths and deaths from crowding. But by the end of the simulation, time 45, it's being solely dominated by crowding. So let's look at this a bit more closely in the model itself. So I'm going to scroll on down, and I'm going to put down a graph. That way I can see the behavior of population a bit more closely. So I click the graph tool, I click again to put it down, and I'm going to scroll down so that I can see both my graph and my stock and flow model. So now you may be saying, well, how do I add a variable to a graph? The easiest way to do it is to command, drag, press, and hold, and watch your cursor turn to a green plus over the graph and drop and let go. But there are other ways to do it. So I double click on the graph and I go to the panel, and you'll see that I've got population in here, and I'm going to remove it. And you'll see that I got this green plus. Anytime you've seen a green plus in the panel, it means that you can add something to this output device, or that input device, or into that input, whatever it is. And when I click that, it says, well, Billy, what variable do you want to plot data for? And I say, Stella, I want population. Now we have multiple different kinds of graphs. We've got area graphs and bar graphs and box and whiskers and bubbles and confidence charts and correlation charts and pie charts and pyramids and scatters. In this case, I just want a line chart. But I want this line chart not to just show me the behavior over time for this run, but I want it to show me the behavior over time for all of the runs. So every time I ran the model, it saved that data for me, and it's kept all of that here. And so it shows me the first time I ran the model, I had population exploding, and I could press and hold on this graph, and at time 100. The second time I ran the model, I ended up at 528. The third time, I ended up at 580. Let's say I don't want to see all those anymore. I can hit this handy-dandy button down here called Restore All Devices. It flushes all those runs away, throws them in the garbage. And now I run again, and here's my population. Cool. So now let's go through a little bit of the validation process. We did some of the structural validation by making sure that our feedback loops were the same feedback loops that were in our dynamic hypothesis. And we did some of that structural validation by making sure we got the right behavior for the right reasons. Because we looked at all of the loops here and their influence on the behavior of the model. And, it makes sense that in the period before what's known as the inflection point being where the growth in population changes from being exponential to being logistic, right about here, it's being dominated by the reinforcing process, and after it, by the balancing process. So now what we want to do is we want to behaviorally validate this model. So what we're going to do is we're going to go back to our reference mode, and we're going to take this variable and we're going to select it, and we're going to copy it. Edit, copy, and we're going to go back to our stock and flow diagram, and we're going to click and paste it. Okay, and now we want to plot population against the reference mode. So I'm going to make this not a comparative graph anymore, because when checked, this graph will display data across multiple simulation runs. We don't want that anymore. Now we want to compare population to reference mode population. And when I run now, you can see, ooh, there's some differences. My population isn't exactly the same as my reference mode. I want them to be the same. How do I do that? Well, you'll see that Stella puts these little handy-dandy knobs on all of the parameters in your model. So we can start adjusting these knobs, and as we adjust these knobs in real time, the model is simulating each and every combination that you enter in. So these models run fast enough that as you drag, it's simulating. And this is what's called Stella Live. So we're using Stella Live now to dial in or calibrate the behavior of this model. And so now we have our model reproducing the history that we got from Excel. And when we come up with a set of parameters that we're happy with, you can see the values above them, but they haven't yet been directly entered into the equations. If we want to enter these values into the equations, we can use what's called the data manager. So if you look in the bottom toolbar, you'll see the stack of disks, which is the data manager. I click to open it, and the run that I'm currently working on is run 4. And there's a button here called Use Parameters from this run, and I click it, and I hit OK, and close. And now, when I go back to edit mode, so I'm going to go back and click on the pencil and paper, and I double click on average lifespan, it's using that value that I dialed in. And when I click on birth rate, it's using that value that I dialed in, so that when I restore and rerun, I get exactly the same behavior that I used to get. So at this point, I'd like to take a breath, and I'd like to invite you all to enter any of your questions into the question area of GoToWebinar. Thank you.
Thank you, Billy. So far, there are no questions, but there was a confusion earlier about how you make the loop panel show up.
Certainly. So let me cover that again. So when you're in edit mode, there is no loops panel. And that's because in order to get all of the information that's in the loops panel, you need to run the model. Okay? So you'll notice if I double click on nothing, I get to the model settings, and you'll see that I have checked off this thing called calculate loop dominance information. That needs to be turned on, and then you need to run your model. And when the model is done simulating, the loops panel will automatically show up for you. So you can't go to like window, open loops panel. You've got to make sure that you've turned on the calculation of loop dominance information and that you've actually run your model.
Thank you, Billy. There's a question whether there are any good reference materials to learn about modeling for high school students.
Yeah, there's a whole bunch of nice materials out there. I know in our store we sell some of the books from Diana Fisher about teaching sysdynamics modeling in K-12. The kind of standard textbook for modeling, but not quite at a high school level, is Business Dynamics. But Kareem, I'm sure you can speak to some of the other resources that exist, particularly at the high school level.
Yeah, there are a lot of resources, for example, at the Creative Learning Exchange, but the best thing I know for high school students were was Modeling Dynamic Systems by Diana Fisher, which she wrote specifically for high school students. There's a question here about how you add the reference mode, I think, to this model to compare against, I think is what they're asking.
Yeah, no problem. Let me do that again. So I'm going to delete it out of this model. And I'm going to go back to my original model that had the reference mode where we brought in the data from Excel in this graphical function. So I select this variable and I copy it. I can do edit, copy, or Command C or Control C if you're on Windows or Mac. And then I'm going to go to Window, Stock and Flow Diagram, right click, paste. So now I have that variable in this model. But now what I want to do is I want to make sure that I can add this variable to this graph. So I double click to open the panel, and you'll notice that my graph is not marked as comparative. That's a good thing. If you had left your graph marked as comparative, you'll notice that the green plus is gone, and if you try and command drag in, it won't, it switches the whole variable out. That's not what we want here. So I'm going to Control Z to undo and undo. Okay, so what I'd like to do is uncheck comparative, and then I can add it to the graph by hitting the Add New Series button or command dragging it into the graph. Once I've added to the graph, you'll see that I've got the blue line for population and the red dotted line for reference mode, but it hasn't simulated that variable yet. So I just hit the Run button, and now I get both.
Thank you, Billy. Somebody asked about calibration. Can you only turn the knobs, or is there some way to calibrate the parameters?
Yes, so we have built into Stella optimization engines, and I say engines because there are multiple of them, that do the hard work for you of turning the knobs to find appropriate values. That's built into our model analysis tools, which is the third panel here in the default panel. And you'll see that we've got sensitivity, payoff, which is the objective function of the optimization, which when you're doing calibration is minimizing the squared error between your external data and your model calculated data. And then in the optimization panel, you can give it all of the parameters that you want to adjust. in order to minimize that squared error between the model and data. And we've got, like I said, multiple different optimization engines built in. The two most important of them are Powell, which is a gradient descent method, and differential evolution, which is a global optimizer based on a genetic algorithm.
Thanks, Billy. And there's a question about whether you could explain the difference between model validation and calibration.
Yeah, so calibration to me is just one small, tiny part of model validation. Calibration answers the question, is my model capable of reproducing the reference mode? But that is just one step along the way, because modeling, the common mantra is structure causes behavior. So you want to make sure that not only is your model capable of reproducing the reference mode, I forgot what mathematician said it, but I think they said something along the lines of, give me 3 parameters, I can draw an elephant. Give me 10, and I can make him waggle his trunk. I'm sorry that I butchered that quote. But the point of that is you can have a model that does a really good job of reproducing history that has nothing to do with reality, that would then give you no reason to trust that model's projections in the future. So part of your validation process is, yes, reproducing history, calibration. But the more important part of that process, at least to me, is making sure that the structure is appropriate, that it's reproducing that behavior for the right reasons. That's what Loops That Matter and the Loops panel is all about. And also that your model is robust to all of the different sets of policies and assumptions that could be made. So beyond calibration, behavioral validation includes things like sensitivity analysis, extreme conditions testing, looking at the values of parameters and coming up with uncertainty bounds around them. So validation is a very, very involved process. The general, root source of information on validation is the Yaman Barlas article, published in 1996 in the System Dynamics Review, and that's really a good place to get started if you want to begin to scratch the surface of model validation within System Dynamics.
Thank you, Billy. Someone's asking how they can see the equations for the model, and they specifically are referring to whether they could see them below the stocks and flows themselves, which we don't do, but how could they see the equations?
Yeah, so if you want to be able to see all of the equations in a list, as opposed to individually clicking on every single variable and writing it down in a text file, we offer a handy-dandy thing called Model Equation Viewer, which then, by default, plots out all of the equations in a table, showing you all of the values, all of the units, any documentation, any annotation. If you want to see them in an order of execution form, you can see them in this much more technical format. If you want to see them in alphabetical order in a textual format, you can do it like that. If you want it in the table, you can uncheck that. And then, of course, you can export this to a file or to the clipboard in order to copy and paste it into any other documents that you're working with. I also believe that there is a free and open source tool called the one by Nacho Kareem, that lets you produce high-quality model documentation.
SDM Doc.
Thank you. I forgot its name.
And it does work with these models. Okay, there's another question here about if they change the run specs from 0 to 100 to 2000 to 2100, will it change the behavior?
In this case, no, because we don't have any time-dependent equations. So let's do it. So let's go 2000 to 2100, restore and rerun. We see that population hasn't changed at all, but the reference mode has. Why? Because the reference mode is the only variable in this model that uses time in its equation. So if we wanted to fix that, we could do time minus the start time so that we don't have to adjust all of the points on the x-axis here. Restore all devices, rerun, and now we get back to exactly what we used to have, just being offset by 2,000 years.
Thank you, Billy. There's a general question about how long it takes to learn to model.
Bob Eberline has a funny quote. He says, modeling is a 10,000 hour skill. But to me, that's to become, a top level expert. There's a lot that you can do with a little bit of training. And we offer a handful of training courses kind of targeted at different levels of modeler, everything from beginners to intermediates to more advanced, covering topics that are appropriate for modelers of that skill level. So to become, a PhD in system dynamics, yeah, you're going to put hours and hours and hours and years and years and years into it. But to solve a problem that's affecting you in your business or in your organization, that's not something that you need to dedicate, years of your life to. At least I hope that we've made these tools easy enough and that we've made the methodology approachable enough to be able to solve the kinds of problems that most people want to solve without having to dedicate themselves to that level and to that extent.
Someone asked if there's a guidebook to learn Stella from IC Systems, and of course there's the Intro to Systems Thinking book that we sell, and there's the online documentation, and there are our webinars, our free webinars, right?
Yep, and then I believe some of the courses that I was just referencing, I think would also kind of cover that same domain. They go through in a bit more detail and a bit slower than I did today. Some of the other functionalities in the software, from sensitivity analysis and modules and arrays and all of these other functionalities we didn't have time to talk about today.
Thank you, Billy. And some of those are in our list of free webinars as well.
Yes, not everything is hidden behind a paywall.
Okay, I think that's it for our questions. Thank you very much, Billy.
Thank you, everybody, for spending either your morning, afternoon, or evening with us. I know I greatly appreciated your presence, your questions, and your interest in Stella and IC Systems. Thank you, and have a wonderful day.